Okay, so welcome to section 2.3, which is applications of static trigonometry. So applications of static trigonometry. These are big words, but don't worry, it's not that difficult. Trigonometry. Static just means stationary. Okay, so let's recall. What do we have? So recall. If we're given right triangle ABC, so given right triangle ABC. Oh boy, that's a terrible B. Let me write that better. A, B, C. So let's go ahead and draw right triangle ABC, like so. Okay, so remember A has opposite side little a, B has opposite side little b, and C we always want to have as the hypotenuse and the right angle. Okay, so what do we have as far as, let's see, what color should I use? Let's do orange. Sine of, let me go ahead and put alpha here. Sine of angle alpha is going to be what over what? Sine for triangle trig is always opposite side over hypotenuse. So the side that's opposite angle alpha is A, and the hypotenuse is C. Okay, so we can be really explicit about that. That's opposite OPP, opposite over hypotenuse HYP, hypotenuse, just to drive the point home. Now let's do cosine. What color should I use for cosine? Let's use this color. So cosine of angle alpha, let's use the same angle. Cosine is adjacent to the angle, meaning what does this angle cut through? It cuts through side B. That's what it's adjacent to. So it's adjacent over hypotenuse. So let me be explicit about that. Once again, ADJ for adjacent. ADJ over hypotenuse HYP. And tangent just comes along or is a result of the two above. I can just take the quotient. Let me move this to the right a bit. Maybe I should move this up. So tangent, let's use green. Tangent of angle alpha. Well, if I take the quotient of the two guys above it, I notice that the c's reduce and I'm left with a over b, which is actually opposite side over adjacent side. And of course the reciprocal functions follow suit. So I'm actually not going to explicitly write them. Hopefully you know them by now. They would be cosecant, secant, and cotangent respectively. So let's also recall, maybe in this color. So also recall that theta equals to 0 degrees. So theta being equal to 0 degrees is flush with the positive x-axis, right? So with the positive x-axis in what form? In standard form, right? Positive x-axis in standard form. So what I'd like to do is annotate some of the angles in standard form. So let's write or draw a little x and y coordinate axes. Something like so. I don't know if I broke this up evenly, but we'll get the idea. Nope, maybe I should have put that up one. Let's see. Is that? Yeah, that looks better. Okay, so we have our x and y coordinate axes. What happened? Why is this? Let's delete this. I don't think it's straight. There we go, that's better. Okay, so we have 0 degrees along the positive x-axis. Actually, I'll still need to move this down a bit. Down 1, like so. Okay, so if I go to here, 1 quadrant, this would be 90 degrees because that's a right angle. Okay, so now if I went 2 quadrants, this is a straight angle, and we know straight angles measure 180 degrees. And then if I go 3/4 of a circle, wow, do you know, that's the worst circle I think I've ever drawn. And I'm not even drunk. Okay, let's see. I'll turn half here, half here. Nope. Okay, I am caffeinated, however. Remember when I said I'd give up caffeine? Well, that didn't happen. So this would be 270 degrees. And full circle is 360. So actually going full circle, and I'll do that here. It's easier to do there, would be 360 degrees. Okay, so hopefully this makes sense to you guys. If not, yeah, we can go by multiples of 90 if that would help. Maybe that would help. So if it doesn't make sense, just remember 1 quadrant is 90. So another quadrant is another 90. So what's 90 plus 90? It's 180. Then another quadrant, or right angle, is adding 90 to that. So 180 plus 90 is 270. Going another quadrant is adding 90 to that. So 270 plus 90 is 360. So we can increase by 90s, and this method of increasing by a fixed angle is going to come into play in the next chapter. Okay, so definition. So I've got a 2-part definition here. So the first one will be the angle of elevation. That's what we're defining first. So the angle of elevation. That's what we're defining. So that's the angle made above. So is the angle made? The angle made above the horizon, or horizontal. It's the angle made above the horizontal. And I'll do an example in a moment of what I mean by these. Whereas the angle of depression, so the angle of depression, that's our second definition. Angle of depression is defined analogously, meaning it will be the angle beneath. So the angle made beneath the horizontal. Made beneath the horizontal. Okay, so for example, what do I mean by that? So let's look at 2 cases. So the first case, here's a horizontal ray and let's have this angle alpha. So this is an angle of elevation. Angle of elevation, because I'm elevating upwards from the horizon. Whereas if I have my horizontal here and another ray going down beneath that, say angle beta. So this is an angle of depression. So this is with respect to the horizon, right? So if we think of the horizon, so horizontal. This is our horizontal. Okay, so angle of elevation, we're going upwards from the horizontal, and depression, we're going downwards from the horizontal. Okay, so let's recall, or learn for the first time, depending. So recall that if two parallel lines are crossed by a transversal, so if two parallel lines are cut or crossed, are cut by a transversal line, then opposite interior angles are equal. Interior angles are equal. Okay, so let's look at two parallel lines. One line here, let's call it L. Actually, do you know what? Let's use some color. Black is getting sick of just monochromatic. There we go, nice colors. So we'll call this line L, and let's call purple line M. So these are parallel lines, and I'm going to cut them by a transversal. Let's call this, I don't know, T, shall we? So line T. Okay, so T is a transversal, L and M are parallel, and what it means that alternate interior angles are equal is that this angle right up here, let's call it theta, will be the same as this angle down here, which is also theta. So alternate interior angles are equal. That's called the parallel postulate from Euclid. Okay, so now that we're done with that, let's do some examples. So for example, suppose you're at the top of a hill. So suppose you are on top of a hill. In the days when you were allowed to go hiking, and you see a cat walking, and you see a cat walking below at an angle of depression. What shall we do? Of 30 degrees? If the hill is 600 feet high, how far away is the cat? How far away is the cat from you? Okay, so the first thing we want to do whenever we have word problems is highlight. So the first thing I know is 600 feet. 600 feet is how high the hill is. So I'm just going to go ahead and say, okay, so this is 600 feet. I know the angle of depression. Now first we need a horizontal. So you're on top of the hill. So this is the horizontal. And I know it's going to go down because it's an angle of depression. So you are right here. Okay. And the angle of depression turns out to be 30 degrees. So that means as measured from the horizontal downwards, This is an angle of depression, so I'm beneath the horizontal. Okay, so if that's 30 degrees, and this is a right angle here, then I claim that this is 60 degrees in order to get to 90. 30 plus 60 is 90. Okay, so I want to find the distance D. What color shall I use? Let's use red. D, to get to the kitty cat. What's the kitty cat? It's right here. Okay, because you've got supersonic eyes when it comes to kitty cats, or at least I do. Okay, so how am I going to do this? That D looks like the hypotenuse in a 30, 60, 90 right triangle, because if I were to complete this triangle, this would be 30 degrees, and this right here would be 90 degrees. So I know that the ratios in a 30, 60, 90 right triangle are short side 1, let's go here, 1, to long side √3, to hypotenuse 2. Okay, well I know that the short side, what color should I use? Measures 600, so I would need to multiply the purple one by 600 feet in order to get 600. So distributing 600 to each number in this ratio would give me 600 to 600 √3 to 6 times 2 is 12. So 1200. So this is my distance D. So the hypotenuse D is 1200. So the cat is 1200 feet away. Okay. So hopefully that makes sense. Let's do another example. Okay, lots of writing for a very simple answer when all is said and done. Okay, so how tall is a palm tree? Palm tree. If, when looking at it, at its top from 300 feet away, 300 feet away from its base. The angle of elevation, meaning I'm looking upwards, so the angle of elevation is 45 degrees. Okay, so we've got, let's see what we have. We're 300 feet away. Okay, so I'm 300 feet away. feet. This is where I'm standing. Okay. Oh, wow, do you know what? I probably shouldn't have made it that large. Just realized I don't have enough room there. Okay, my angle of elevation. So angle of elevation is 45 degrees. So it's 45 degrees to the top here. So this angle here from the horizon, right? Let's write this. This is the horizon or horizontal. So 45 degrees above the horizon because it's an angle of elevation. And then we have our palm tree. Okay, so the top of the palm tree is at an angle of elevation of 45 degrees. Okay, there's our palm tree, something like that. Right, note. Okay, well, it should be evident that this is a 45, 45, 90 right triangle because this is a 90-degree angle. So therefore, I want to know the height of the tree. So how tall is this tree? So that would be the length of this side here. Agreed? So we're in a 45, 45, 90 right triangle. So the ratios are 1 to 1 to the square root of 2. But I know in order to get the base, which is a purple guy, to measure 300, I would need to multiply this ratio through by 300, giving me 300 for the base to 300 for the height to 300 root 2 for the hypotenuse. But I was looking for the height. So this is the height. The height is 300 feet. That's one heck of a large palm tree. Clearly, I wasn't thinking when I made this up, but you get the idea. We call it this is a magical palm tree that helps you do math. How about that? Okay. Okay, so definition. Okay, so bearing, that's what we're defining. Bearing. So is the measure of an angle with respect to, so is the measure of an angle with respect to WRT, with respect to north, which we're going to annotate as capital N, or south, which we're going to annotate, of course, with the capital S on a map. On a map, and is given by so the way we do this is first direction. So first direction, then angle, and then second direction. So what do I mean by all of that? Well, for example, so let's plot the following bearings. So plot the following bearings. And state the corresponding angle in standard position. So and state the corresponding angle, theta in standard position. Okay, so number 1. Let's say I give you north 30 degrees east. So what does this mean? So this is first direction is north. The angle given is 30 degrees, and the second direction is east. Okay, so let's do x and y coordinate axes, which will be directional axes now. So x and y normally. So this is east and west. This is north and south. Okay, so what a bearing means is we start at the first direction, and then we go towards the second direction. So let me do, oops, oh my goodness, what's going on? Okay, no, go back down. So we're going towards east. So what does that mean? We start at north, and we're going to go 30 degrees to the east. So 30 degrees. So our bearing is going to be here. We started up at north, and we ended up going 30 degrees towards the east. Okay, well that must mean that the remaining angle down here, what color should I use? Maybe orange. So this angle down here must be 60 degrees. So that is our theta in standard position. So theta is equal to 60 degrees. That corresponds to the bearing north, and then go towards the east 30 degrees. Okay, let's do another one. So subscript number 2. Let's do north 70 degrees west. Okay, so once again we have north is the first guy, which tells us where to start. Then we're going 70 degrees to the west. So if we have our, let's see if I can copy and paste. Yeah, it works. Okay, good. Okay, so I start at the north, but now I'm going 70 degrees to the west. So this is now 70 degrees in the direction towards the west. So I don't like this. Make that a bit better. Okay, so my bearing now, which is over here, is going to be, do you know what? No, that doesn't look good. Let me make this a bit better. I know that for 90 degrees the difference will be 20. So let me make it look more like it's 20. Something like so. Okay, so I'm going 70 degrees from the north towards the west. So that leaves me with only 20 degrees here. But that's not what matters to find theta, because theta is the distance in standard position here. Well, I know if I were to go from east to west, that's 180, so I'm 20 degrees shy of 180. That means I must be at 160. Okay, so theta in standard position here is 160. number 2, or 3 rather. Let's do south 60 degrees east. Okay, so now we're south. We're going 60 degrees from the south towards the east. Okay, let's put this here. So I'm starting now south down here, and I'm going 60 degrees towards the east. So this is 60 degrees here. So my bearing looks something like so. So what is the distance to the x-axis? I know is 30 degrees. Okay, so what is theta? Well, it's almost full circle, except for that 30 degrees. So 360 minus 30 is 330. So in standard position, that bearing south 30 degrees east, south 60 degrees east is 330 degrees. Okay, let's do one more for good measure, and then we'll be done with this section. So number 4, let's say we have south 45 degrees west. So we start south, then we're going to go 45 degrees to the west from the south. Okay, so we start in the south, and we're going 45 degrees towards the west. So our bearing, which is 45 degrees from the x-axis, so that must mean that I've got 180 plus 45. So I know theta goes half a circle plus this 45. So 180 plus 45 is 225. So in standard position, theta is 225. Okay, so hopefully this makes sense, and I will see you guys in the next lecture.